Good evening, guys. This video will just be a short video regarding Jupiter and Saturn, the first topic on module 3. Um, the slides have a lot of information regarding the two largest planets in the solar system. Obviously, there are some characteristics, like, for example, the rings of Saturn that you will find at the end of the chapter. The key ideas with these two planets is more about their composition, the fact that Jupiter is the largest planet in the solar system. They both are mostly composed or made of hydrogen and helium. They are gas giants. They don't have a surface, but they have a rocky core, which we can imply by their shape. They don't have a rotation, and when I mean rotation, is rotation around their axis, like the Earth, because of the different density and composition, right? The Earth is made of rock. These two planets are made of gas, more like a fluid. So in one of the slides, they explain about differentiated rotation, where the particles in a fluid, for example, when you stir it, they don't move at the same speed. It depends where they are located in the fluid, right? A gas can be considered or can be studied as a fluid. Um, Due to the big mass and the speed of rotation, we know that Jupiter has the shortest day of all planets. So it goes around its axis almost every 10 hours. All right. So this makes for a rapid rotation that flattens the planet a little bit. And it goes around the sun, talking about Jupiter again, every 11.8, basically every 12 years. So it takes way more than the Earth, as expected, due to the eccentricity of the orbit. Remember that even though it looks almost circular, it's an ellipse. It's very important that you know some of the missions. I mean, they start here with the Galileo mission that arrived to Jupiter in 1995. See how long it takes, 6 years in there. It's quite a lot. It depends on, like, as you know from the previous chapters, on where, when, and where is Jupiter located in its orbit. It can be in conjunction or opposition, so there can be a huge gap in terms of the or a huge difference in the arrival time. But 6 years seems to be like, or 6 to 8 years seems to be like the average. Um, but there have been other missions: the Voyager, Voyager 1, Voyager 2, the Pioneer, and now the Juno mission in 2011, right? They've all been sent to Jupiter. And they always have to be careful when we do that, because as you will know from the slides, and well, I can mention that, or in the video that I posted in the module, Jupiter and Saturn have very strong magnetic fields, like a shield. So whatever approaches Jupiter will feel that, and we have to take that into account for a very close approximation. Obviously, the main characteristic of Jupiter is that red spot, right? Which is a huge storm in Jupiter that has been there for almost 400 years, and it's so big that almost 3 entire Earths can fit in the spot, and more than 1,000 Earths will fit in the whole planet. That's because of the huge size. Now we know already that because it's mostly made of gas, the density is way less than the one on the Earth. It's 1,326 kilograms per meter cube, while in the Earth, for the rocky planets, it's around 4 to 5,000 kilograms per meter cube. There are some important questions here, like what kind of particles are in the rings of, well, you should know by now that every Jovian planet has rings. The most prominent ones are the ones in Saturn, but Jupiter, Uranus, and Neptune, they also have a set of rings. We should also know the structure. So we're talking about the interior of Jupiter, which is made of rock, but also metal and hydrogen compounds, and a particular state of matter for hydrogen, which is liquid metallic hydrogen, which is responsible for the high magnetic field. Something that we should also correct, not from the slides, but in general, is here is the differential rotation, all right, because of the different composition. So that is important is not just the nature of the storms or clouds, as you can see in the forms of the red spot or the belts, the dark belt, the bright belts. These are pictures from, for example, here you have from the Hubble telescope. All right, and look at those small sort of mini red spots, right? Which are all storms. This is from the Pioneer in the 70s, right? Way beyond the Galileo and the Juno mission. But look at the clouds in there and look at the overall structure, right? Um, the upper atmosphere of Jupiter is divided into cloud belts and zones. They are made primarily of ammonia crystals, sulfur, and mixture of the two compounds. Okay, it's important to notice that what you see right now is what is basically on the upper atmosphere. As we go in, and we have actually sent, and if I remember correctly, it was the Galileo mission, the one that they sent, and then they managed to make it go in until they lost transmission. The idea is to basically see what's going on, and it's a chaotic environment where, as you go in, the pressure and the temperature increases a lot. But also, the planet's composition is different. We will see that in a bit. Normally, Jupiter used to be called a failed star in reference to what we call brown stars in astronomy, that you will learn more in Astronomy 102. Even though it's true that, like a star, Jupiter is rich in hydrogen and helium, Jupiter does not have nearly enough mass to trigger fusion in its core, which is the characteristic of every star. Now, normally the way a star generates energy is by fusing hydrogen atoms into helium under extreme heat and pressure. All right. For Jupiter to ignite this nuclear fusion, for example, it will need more than 70 times its current mass. So it's not really a brown dwarf, right? A brown dwarf is a failed star, but it will have way more mass. I believe around 18 times more mass than Jupiter. So it's way beyond, way outside the limit. Now, Jupiter and also Saturn, but more Jupiter, and you probably have seen it, it can be seen with a naked eye. All right, depending on the time of on the time of the year. Now, both are flattened because of the composition of itself, because of the rotation, and because of the enormous force of gravity, right? But Saturn happens to be the flattest planet in the solar system. Its polar diameter, the diameter on the pole, like on the north or south, is about 90% of the equatorial diameter, right? So it's almost very flat. It's like basically saying that 90% of what you have on the top, like it's not the case of the Earth, right? Is 90% of the whole planet in the equator, right? Now that's normal. That's due to the low density and the fast rotation. Similar to the case of Jupiter. Saturn turns around its axis every 10 hours, so almost like Jupiter, and it has the second shortest day in the solar system, as expected if we compare it with Jupiter. And here is the composition I was talking about. You have the liquid ices surrounding the rocky core, and then you have the helium and liquid metallic hydrogen in what will be the mantle here on Earth, right? And the crust, sort of, not really, because it's deeper than that, is where you have the ordinary hydrogen and helium clouds. That's the upper atmosphere, right? So the same as Jupiter, Saturn upper atmosphere is divided into bands of clouds. The top layers are mostly ammonia ice. Below them, the clouds are larger, are mostly water ice. And below are layers of cold hydrogen and sulfur ice mixture, so similar to Jupiter. So remember, both Jupiter and Saturn, they have bands and cloud bands and zones. And mostly those clouds are made of ammonia ice, water ice, and below that, hydrogen and sulfur and mixtures of those. And then below that, you will have the liquid and helium metallic and the liquid metallic hydrogen, basically, which because of the fast rotation, it creates a very strong magnetic field, as it says in this slide. In terms of moons, we know that Jupiter has we have found at least 73 moons, and Saturn has 150 moons and smaller moonlets. Okay. There is a different video I'm gonna post about the moons. It's not gonna be that long, but I think it's appropriate, and I think you guys should watch that video as well. But it's important that you guys watch the video about the Galilean moons, because these are far more interesting places where we have actually spent time investigating. For example, Io, a volcanic moon, Europa, due to the ice covering most of its surface or all of its surface, Titan, Rhea, Enceladus, Ganymede, and Callisto, right? So those are moons where we can potentially maybe find some sort of organic life, especially Europa. So I will be discussing that in the next video. For example, here I can say that Titan is a moon that you know has a very dense atmosphere of nitrogen. And in the case of Saturn, right, we have the Cassini missions, the Voyager missions, and the Pioneer 11 that have investigated it. And the Cassini actually orbited Saturn from July 2004 until September 2017. So just a few years ago. So now we can talk about a little bit of the rings. So as you can see, there is a system there, A, B, and C. There is actually more, but the reason why we have this free is because of the Cassini division there. The rings are basically made of ice, are very icy objects orbiting around Saturn. All right. The rings were discovered actually by Galileo Galilei in 1610 when he was observing them through the telescope. But the first close view was actually with the Pioneer 11 in 1971. Don't worry about the years, but more about the missions. All right. The Pioneer, for example, in this case. And I think it's very important that we talk about the rocket limit, which is basically the point, the gravitational point where you can find objects orbiting around a planet. It's not like Lagrangian points in the case of the Earth and the Moon system. But in the case of the rocket limit, we have to take into consideration the different density of the objects. So as it says there in the slides, it's approximately 2.4 times the radius of the planet, provided that the material orbiting the planet has the same density as the planet itself. If it has more density, so more rocky or icy material, it will be closer to the planet. So in general, Saturn rings are made of billions of particles, from tiny dust grains to objects as large as mountains, okay? So I show you 3 groups, but normally we know that Saturn rings are divided into 7 groups, A to G, and we have 2 divisions actually. The Cassini division, but there is also the Equate, I believe, division. Oh, it's not here. Oh, Equate gap there. And that's where you have the F division there, F ring. Saturn's atmosphere is composed primarily of hydrogen and helium, just like Jupiter, with traces of other substances like ammonia, like methane, and propane. Okay. All right, guys. So it's not a lot about these planets, to be honest. I want you to take a look at the key ideas, and I want you guys to watch this video about Jupiter and Saturn, take a tour. The quiz on this chapter will be very short, and then the following chapter also about the satellites. The next chapter that I'm going to publish today is going to be about Neptune and Uranus, and then you will have another chapter about the vagabonds, the asteroids and comets in the solar system. And then that will be it for this course. All right. Expect another video to be posted this weekend after Thanksgiving, and then next week the other video about Uranus and Neptune. So if you don't have any questions, my advice will be that you guys start working and finishing exam number 2. There should be 2 more quizzes and 1 final exam to finish this online astronomy course. All right, guys, have a nice Thanksgiving. and see you in the next video. Bye-bye.